really clear. We were supposed to have a test. I don't know, sometime that was it today that was supposed to happen? Yesterday. Yeah, so how'd that test go for you? I don't know, right? Right? We will test the next time I see you, whenever that is. So if we have school tomorrow, then we will test tomorrow. If we have school on Monday, but we don't have school tomorrow, like whenever I see you next, we will test. Does that make sense? Sure. So whenever that is. I felt like just throwing you into a test after I haven't seen you for a week seems kind of I know, like it just doesn't seem like a nice thing to do. Yeah. Right. So hold on just a second. Isaac, I see your hand. Hold on just a second. Let me just kind of say this. So the next time I see you, we will take a test. Depending on how long the periods are, it might be like part in class and part out of class. I will adjust that. I was going to print it last night, but then I'm like, I'm just going to wait and see. So I have it, but it's not printed because I will adjust as I need to. Okay. But just know that the next time that we have class, we will take a test over simple harmonic motion. Boom. If there is no school tomorrow, because with all of the snow days, the AP test date does not change. Okay. I will send you an email sometime before 9 a.m. with something. That doesn't mean like it's going to be a full lecture that you have to take notes on and all of that sort of thing. But we need to keep moving. Do you know what I'm saying? So I will find something for you like that will move us in the right direction. Luckily for us, the stuff that we're going to move into for a little bit here is pretty qualitative and not a lot of like super hard math. So that'll be nice to kind of like, if we need a little bit of buffer, we will do that. But please check your email by 9 a.m. tomorrow, and we'll figure out what that will look like. But that'll give you a little time to kind of process that once we know what it looks like. Okay. My plan for the day today is to entertain any simple harmonic motion review stuff or questions that you have. You've had a few days to look over things, so maybe you've developed questions or maybe you've figured it all out. I don't know. And then if we have time, and I hope we have some time, but if we don't, that's okay. I've got some kind of starting on the next set of stuff, okay? Which will kind of, it moves very seamlessly from what we were doing before. So it won't be like a total juxtaposition for you, okay? Yeah. Questions about logistics? Does that seem fair?
Yes.
Fantastic. Yes.
Are we like still on schedule?
We are.
No more doing it.
We are. When I paced it out over winter break, we are now 1 day behind. But I did build in a few days of review. Does that make sense? So we've just got to keep cruising. But like I said, we'll get there. We'll be fine. Like, you know, I have taught AP Physics 1 while being on maternity leave for 8 weeks at a, so like we can do it. We'll be okay. I don't intend to be gone for 8 weeks anytime soon, so I think we should be fine. But yeah, we'll be okay. Yeah. All right. Anything else? Isaac, I saw your hand earlier, and then what's that? Okay, perfect. Okay. Any other logistical stuff? Questions about simple harmonic motion that you guys want to talk about? That's my next thing to talk about if you have questions.
Well, I'd like some help on this grade sheet. But
okay.
Yeah.
Is that this stuff?
This one.
Yeah, this one.
Yeah.
All right. This one? Or the other one?
Well, I have questions on both sides.
Okay. So, friends, I know it's been a while. I totally get that. Again, this is why I didn't want to test you today. Pull out it's the little green half sheet. It's got 2 graphs and some questions on energy. Instead of me going through it directly, I'm going to open it up to get help from everybody. Does that sound okay? Not because I don't want to talk to you about it, but because I think it's good review for everybody. Okay? So, everybody get that sheet out. I think everybody had one. Were you all ready? Do you need one? Because I don't think I have them, but I can find one for you. Okay. Do you have a preference on which one you start on, Courtney?
No.
Okay.
Fine.
We'll start on that one because it's up there right now. All right. So should we just go through it? Is that what you'd like to do?
Sure.
Okay.
I got part A, but a refresh would be fantastic.
Sure thing. All right, friends. So taking a look, it's like I said, it's been like a week, or maybe you've been studying it every day. I don't know. Energy. So spring potential energy versus displacement squared. One of the reasons I like this is just to make sure that you're paying attention, right? And it may have taken you a little while at one point to notice that that was displacement squared. Hopefully you saw that. I don't know. All right. The graph shows the variation of the square of displacement with potential energy of a particle of mass 40 grams, executing simple harmonic motion. Use the graph to determine blah. So one thing to know, because I know that a couple people asked is this a mass on a spring? Is this a mass that's swinging? I don't think I mentioned this to you before, but there's another really fun example of simple harmonic motion that is very theoretical, not actually physically possible. But I don't know if when you were a little kid, you ever like imagined or you read a silly story or something like that about drilling through the center of the earth and like sending notes to people on the other side of the earth. I don't know if that's ever something that you've like ever imagined or thought of. So here's the fun thing, is that if you literally were able to bore a hole through the center of the earth, okay, and you dropped a little message because you had a friend that was on the other side of the earth, and you dropped that message, so if you drop it from high above, so if my hole is right here and I drop it here, then it will make it as long as your friend's ready to catch it. Otherwise, what's that message going to do?
Burn.
There's a bouncy, 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 bouncy. So I have a hole. I know, right? It's weird. What force is causing that harmonic motion? It's gravity. It's the fact that gravity varies with depth because you've got a different amount of mass that's pulling on it. It's weird. But it would go bouncy, 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 and it would exhibit simple harmonic motion in the same way that the mass on a spring exhibits simple harmonic motion.
This yeah.
It's kind of crazy. Yes, its equilibrium would be the center of the earth, but at that point there's no force, but at that point it's still moving, and so it's just going to keep going and going and going. It's kind of weird. Anyway, point of that, number one, was to just share that with you because I forgot that I hadn't done that yet. The other reason I wanted to mention that to you is that it does not matter which type of simple harmonic motion you're looking at. Okay, they all follow the same rule, and that's what I want to make sure that you know. Okay, so they all follow that same F is equal to 1 over 2 pi blah 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 blah. Right? So just FYI that is true. Okay. Whew. All of that said, how do we do this problem? Part A, a good review.
Well, lead us to the battle. Actually, that's a very good question. Let's see here. What did I do?
Nick, did you want to say
A
something?
lot of stuff written. You want to go for it?
Do it. You picked a point on the graph. 1 comma 20. Seems like a reasonable point.
And so I set a potential energy formula to find the theta value.
So PE sub S, that one, equals, yeah, bless you.
X is just 1 because the square root of 1 is 1.
So that's easy. So that was a clever choice. Yep.
And I got the theta value to be 40.
Okay.
And then I plugged that into the omega equation.
Okay. Omega equals, bless you,
Bless you.
K over, is that what you're doing? K over M? Yeah. I just want to make sure you were, yeah, I just couldn't hear you very well. Yep. You got your mass and you got your K. Okay.
And then I found the value for omega, and it's 2 pi over omega.
And then period is equal to 2 pi over omega. Does that seem reasonable? And what'd you get for period? 0.063 seconds. Huh? Is that okay?
No.
That's not what I got.
That's what I got.
Wow.
I don't know. Maybe I messed up too.
What'd you get for omega?
What'd you guys get?
31.62.
I got 100.
Yeah, we got 0.1.
You got what?
We might be wrong.
0.199?
Yeah.
How did you do it?
I think we used the.
That's what I got.
So talk us through.
Long time ago.
It was. But you're going to have a test the next time I see you, so this might be on it. So, you know.
Oh, it looks like we used 1 over F.
1 over F
Yeah.
equals period. Okay.
And then we used the equation for F.
Okay.
which is 2 pi over times the root of,
Isn't it 1 over?
yeah, my bad.
1 over 2 pi. I just want to make sure, because sometimes we make little silly mistakes, and those little silly mistakes can propagate really well. So I want to make sure that, yeah. So 1 over 2 pi times the square root of k over m.
Yeah.
Mm-hmm.
And then we plugged in the values. We used the slope of that graph.
You use the slope.
Wait, no, we used the k formula. I don't remember. I didn't write down any of it.
Okay. Well, somebody that has something written
I
down,
have
help us.
all of this written down, that's why I'm.
The blue stuff or the red stuff or both?
Yeah.
Because the blue stuff and the red stuff are the same. That's
Yeah,
why.
we did use the slope. We did use the slope.
Go for it.
Yeah.
Okay, so I took omega equals square root of k over m,
Okay, hold on. Square root of k over m. Yep.
and I got 31.62.
Okay, now hold on just a second. So where did you get k of 40?
Yep.
Okay. Over a mass of,
Yeah, 0.04. I think.
Yeah.
Yeah, we did, we changed it to.
okay.
And then, so then I used f equals omega over 2 pi.
Yep. Which is the same thing here. Yep.
Yeah,
So let's see if our omegas match, because maybe that's where the problem is, huh?
No, yeah. We used the graph. We used the slope and then doubled it.
You used the slope and then doubled it,
Because the slope of the graph is 1/2 k.
right? It's the same. He did the same thing.
Yeah, then we got 40. And then
Yeah, no, that's what I'm saying. So I'm trying to figure out where the discrepancy is coming from.
Yeah.
Wait, so 140 be 0.04, not 0.004? Right?
What? The mass is in your.
What did you get for omega? You got this, right?
yeah.
That's
Nick?
And then somehow I got 5.03.
Did you get 31.62 for omega?
No, I might have made a complication there.
I may have too.
I just did 40 divided by 0.004, and that is 100.
I think that's what I made.
But
Okay.
0.04.
Okay. So let's back up for just a second. So do we all agree on omega is this now? Or no?
Yeah.
Help me out, friends. I'm just facilitating here.
Yeah.
Yes.
Okay. So this is omega. And so if we do that, then we've got 2 pi over that. And I may have made a mistake too, because it happens, right? 31.26 or 62?
It's like 0.2.
Is 0.2?
Yeah, or it should be 6.28 divided by 31.
Yeah, so I think it is that. I don't know where I messed up. I may not have converted too.
I don't know.
Yeah.
I forgot the mass. It was in grams.
I think
that would happen. Did you convert those?
I didn't convert correctly.
Yeah.
I think that's what happened to me. I'm not sure. Yeah. I'm not sure. Did you?
I just 0.004 instead.
Oh, okay. There you go. I must have done the same thing. Yeah.
So it's 2 pi over omega or omega over 2 pi?
It depends on which one you're talking about. So if you're talking about frequency is omega over 2 pi.
Okay. And then you
Period is 2 pi over omega because they're reciprocals.
Oh, so really.
So I was I did the roundabout way, and I found frequency, and then I put it in
Yep. Yep. And all of that's okay. Yep. I think I must have done the same thing as Nick did and just converted. Question?
So that we did it a little differently.
Yep.
We got the K of 40 using the potential energy equation.
Yep.
But then we just plugged, to find the period, we just plugged it back into the period formula, 2 pi times really.
Yep. So you just did this in one step instead of two. That's okay too. Yeah. That I actually, when I did it, besides my, that's what I did too. Yeah. All right. We okay now?
Yeah.
All right. Part B. Maximum speed of the particle during the oscillation?
Yep.
How are we doing that?
Kinetic energy.
It's another great question.
Kinetic energy?
That's what we use.
Tell me. Speak more words.
We plugged in the mass, and we had the final kinetic energy. So it was 1/2 40 v squared equals 80.
Okay. So say it again. 1/2.
What?
The 40 is.
The 40 is the mass.
Okay. So I'm gonna.
Oh yeah, we have to. Yeah.
free piece of information. On your test, there might be something that doesn't say calculate, but says show that. Okay? AP loves show that. Show that this equals this. If it says show that, you can't just grunt and make it happen. You have to actually do physics. Like you have to make it a little prettier. Do you know what I'm saying? So you can't just throw numbers in and hope things come out. You got to do physics. So
1/2 of it, yeah.
I want you to do physics here, not just grunt. So tell me what I need to write down.
1/2 mv squared equals
1/2 mv squared
the final kinetic energy. Yeah, kinetic energy. Right.
equals kinetic energy. Okay. E sub k.
We know the kinetic energy at the end of the thing is 80.
Why?
Uh,
I'm trying to get the physics. What is it?
According to the graph, the maximum potential energy is
Okay. And so there's more physics. There's like a phrase that I'm waiting for.
Conservation.
Yes. Okay. So you can say that the spring potential energy, are we writing that as U sub S? Help me out, you guys. Yeah? I don't remember.
Yeah, either way.
Okay, whatever. So the maximum potential energy has to equal the maximum kinetic energy. And you can say this because of conservation of energy, right? You've got to say that. That's the physics. The rest of it is just algebra. This is the physics right here. Saying that the maximum is there, or you can say kinetic plus potential equals kinetic plus potential. That's fine too. But you've got to say something like this so that I know you know physics. Otherwise, it's just grunting and pushing, right? And that's not helpful. Okay? That isn't physics. So you can say 1/2 mv squared, mv max squared has to be equal to the maximum spring potential energy, right? That's where the 80 comes from. Okay? We're just using this as like a learning opportunity here, right? We know the mass. What's up, Jasmine?
I'm just wondering if you convert kilojoules to joules.
If we need to convert it, or did we convert it? I would say yes. Because otherwise we have things in, funny units. So absolutely, yes. Yeah, I'm not going to guarantee because I can't remember, but I think that generally they try to avoid the millas and centas and things like that. Yeah. Does that get you where you need to go? How fast is it going?
2 meters per second.
2 meters per second. Yeah. So a question on a test might look like this, except it might say, show that the maximum speed of the particle during an oscillation is 2 meters per second. You got the answer. Sweet. But they want the physics, right? Why is that? Yeah. Yep. How are we doing? Yeah. I believe it is. I don't know for sure. I'm just looking now. Let's.
Yeah, the millijoules with the. Yeah.
Do you want me to go through it quick and make sure?
If you want, I got the answer, but that's because I didn't convert it.
Okay.
So,
Yeah. So I think that's probably why. Yeah. Like, did you get like a factor of 1,000 off?
Actually, no.
Like a lot more?
I got 63.
I got 6.2.
I wonder if it has to do with the squared though. Do you want? We can go through it if you want. It's up to you.
Yeah.
Let's do it. All right. So 1/2. No, it's okay. Here. So this is going to be. Let me just write it out here. V max is going to be equal to the square root of what's that going to be? 2 u sub s max over m. So that's the square root of 2 times. So it's 80 millijoules. So that's going to be 80 times 10 to the negative third. I'm just trying to, hold on to everything there. And the mass is 0.04 kilograms. Is that okay? We can plug it in that way, then we won't make any silly mistakes. Does that get us where we need to go? So we've got 2 times. That does come out to 2. Yeah. All right, team. Do you want to flip over to the other one?
Yeah.
Well, that one's really big. Whoa. All right. Let's do it, friends. This one shows kinetic energy with mass. Use the graph to determine the total energy of the particle, maximum speed, amplitude. They love all this stuff, right? Yeah. Total energy. What's the total energy? 80 millijoules. You can find that one fast, right? It goes to a maximum. It's at the maximum. It's got to all be kinetic. Boom. All right. Maximum speed of the particle. How do we do that?
Same way you did the speed on the last
1/2 mv squared.
80 millijoules, though, right? Yep.
Yeah. And so, and then the mass is 0.4 this time.
Yep.
So it's slightly different.
So it's different numbers.
Yes.
Yes. What did you get for velocity?
The root of 0.4. We wanted to keep it exact. What?
Physicists don't keep things exact. Come on. Square root of 0.4?
Yeah.
0.63.
You want to keep, yeah.
That is actually exact.
Yeah. 0.63?
Yeah,
exact?
it is.
I don't know. I didn't want to put my calculator.
Okay. So really, I want to keep it exact means I'm lazy and don't want to push the
Well,
button.
I mean, it's.
I'm just interpreting. I'm not judging.
No, it's not exact. 0.63 isn't exact. He proved it. We're all about accuracy over here.
All right. How about amplitude? 4, right? You can just find that one from the graph, can't you?
Yeah.
D. Potential energy when the displacement is 2. How do you do this one? Go, Nick.
And he the law of conservation of energy, so find the difference. Kinetic energy is 60 at 2 seconds, compared to centimeters.
So 60 millijoules plus U sub S equals the max here, right? It does. Look at us. And then the period of motion. That's silly. Period of motion always comes back. Jeez. Oops. E. How do you find the period? Good question. This is one of those. There are lots of ways to do this problem, I think. Help us out, friends. What'd you say? Yeah. So you did conservation of energy. So you said the kinetic energy max. Guys, I feel like we've digressed a little bit. Can we be quiet, please? Equals the 1/2 kx squared. Is that what you're talking about? And then solve for k. Okay. What'd you get for an answer? Oh.
I got it wrong.
Oh, okay. No worries. Did you guys get an answer for that one?
0.39.
So K.
Oh, wait. Sorry.
So K is the period then? Or
K is the.
You just have to find it.
That's what she's saying. Yeah. Did anybody do it a different way? What did you guys get for an answer for that one? Go through it right now. I want everybody to do it because y'all are like, oh, yeah. Do it right now. Do it right now. Talk to each other. Go, 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 physics. Do it. Let's go through it. All right. So you have 80 times 10 to the negative third equals 1/2. Doing okay? Okay, okay. Chill out. Times 0.04 squared, right? That's in meters. So what do you get for K? I don't know. I did it a different way. That's why I'm asking. Ah, come on, silly thing. So what'd you get for K? Friends, I need you to help me out here. Because if it's just two of us having a conversation, then we're wasting time. Because I can just have conversations with people individually later. Are you helping me? Are you doing this problem? Because if you haven't done this problem, you're going to be sad soon, I'm guessing. So help me out. What did you get for K? Did you get a value? 100?
Yeah.
Okay. And then, what are we doing with that K? Put it in, right? We're looking for period. So period is equal to, it's going to be 2 pi times the square root of m over K, right? You can also write that as frequency is 1 over 2 pi times the square root of K over m. And then take the reciprocal. Are you okay with this? Yeah?
Yeah.
So we know K, we know m. You can also do the omega stuff in the middle if you love omega more. It's fine because omega lives right in there and it's all good. Whatever makes your heart happy makes this work. Okay? So you get 2 pi times the square root. Whoops, I put the wrong thing in there. Square root. What was the mass? 0.4?
Oh.
No, 0.4 divided by 100. What do we get? 0.4. I'm going to come back. I'll be right there in a second to look at it. Yeah.
So the 0.04 is from 0 to 8 meters, right?
Yes. Yes. Yeah. How are we doing? Are we okay? Elizabeth, you look unhappy. And I may have too. So check me because I don't have the answers to these
No,
problems.
that's
what I got.
That's what, okay. So
0.397.
So groupthink tells us this is right, but I don't know. What do you think, Niam? Do you disagree? Do you see a difference? Because I don't have the right answers written down anywhere, you guys. I'm just working these with you. If I made a mistake, help me out. Did you do it this way? Did you plug in? Did you get 100 for K?
Yep.
Okay. Did it come from this, the centimeters? Did you convert to meters? Okay, that would explain that. Are there other simple harmonic motion questions that you all have for me? Yeah.
How much are you giving us? Like,
The yellow sheet that you have?
just on some.
Oh, extra. I won't. I know. I'm. Yeah, I'm not going to give you extra equations. Yeah. Other questions that you have for me?
No. Oh, so not on this, but, okay, so when you're looking at a mass on a spring versus a horizontal mass on, or like vertical versus horizontal.
Yeah.
The only difference is, well, you use the same equations, but the vertical mass takes gravity into effect, right, with the equilibrium position.
Yes.
So that would be the only difference.
Yes.
If on a test you ask, do this for a vertical spring or for a horizontal.
Yeah. So generally, I'm trying to think if I don't want to make a sweeping generalization, but generally when you do a mass on a spring problem, it's going to be like this. Okay. Now and then you would get a very specific mass on a spring problem this way, but it wouldn't be as overarchingly general as this stuff that we just did was, because gravity throws a huge wrench into the whole story, right? The only reason we do that to start with was because Hooke's law is really nice to graph that way. Yeah. And it's hard to imagine a frictionless surface that this is going to balance on, but in physics we like to live in ideal worlds, right? So, yeah. Other questions that you have for me right now?
Question 16 on the homework.
Yeah. I don't have any idea what that was, but I can look it up. Would you like me to do that?
Yeah.
This is chapter 14, right?
Yeah.
And what number did you say
16.
Question 16 or problem?
Yeah.
Question 16 says the young girl and her mother are swinging on the swing set. That one?
Yeah.
Okay, so friends, I am going to read this question and answer it. If you don't care about the answer, if you already know the answer, please be quiet so the rest of everybody can hear. Thank you.
Oh, we got it.
Just go. Just go.
Go. Do it.
Go.
Yes.
No, sorry, I took the time.
Okay. Okay, a young girl and her mother are swinging on a swing set. Who, if either, has a longer period of oscillation? So, what's the difference between a young girl and her mother, we would assume?
Mass.
Yes.
Age.
Will the mass affect the period? No.
It's a pendulum.
So, they don't tell us quite enough information, though, do they? What are they not telling us? The length of the swing. So, my answer to a question like that would be, if the swings are the same length, then their periods are going to be the same length. If the little girl is on the shorter swing, then who's going to have the longer period? And if the mom is on the shorter swing, then who's going to have a longer period? Right. Boom. Does it matter who goes higher? It does not matter who goes higher, right? Yeah. Sure thing. I think we did. I think we spent a lot of time on it because that was the one I wrote up there like a while ago and then forgot to erase. Yes, we did go over that one. The issue was about question part B, and you can solve it with conservation of energy. That's the easiest way. I know that we recorded it, but if you work on it, yes. And if you get stuck, then let me know, and I can work on it with you, okay? Yeah. Anything else that's in your head that you need help with? Okay. So, where did my little pile go? Oops. Whoa, that could have been bad. All right. So what I'm going to do right now, we don't have a lot of time. We have like 7 minutes or something like that. I'm going to go ahead and give this to you. This is what we were going to spend time doing if there weren't questions today. But given Henry's predictions, and I don't know what's going to happen in the next couple of days, I'm going to go ahead and give this to you now, because if I have the opportunity to send you an email before 9 o'clock tomorrow morning, this will be the first part of it, and then you won't have to print it off yourself, since I've already printed them. Does that make sense? So this is kind of like Mad Libs with the right answer, right? There are right answers to these, so don't just put in random nouns and verbs, because that will not be helpful for you later, okay? I will tell you, because every year that I use this, I have students, regardless of if they're 9th graders or if they are 12th graders, they get really, really cranky because they're used to filling the blank sheets where you just look at the book, look for the bolded words, and then you fill them in, okay? I guarantee you that will not be the case. I wrote this about 5 years, maybe 8 years ago, okay, with a very different textbook, and it wasn't even word for word from that textbook. So you'll need to do some reading, you'll need to do some looking things up. I do have a word list that I will put up on Canvas for you, so you can take a look. I am not going to spend a lot of time with this after you've gone through it. We'll go through it fast the day after the next time I see you, okay? That will be our jumping off point, but that will not be where you will, like, we're not gonna go over this in great detail. Does that make sense to you? Okay, so if you wanna start looking at this right now, you can. If you wanna look at some more simple harmonic motion stuff, you can. I would strongly recommend spending some good quality time with, I'm still listening.
That's fine.
This sheet that we worked on for like 3 days, right? I'm not saying you have to have these memorized. I don't mean that. But if you understand this, then you'll be much better off on whatever day it is that I see you. Okay? So, do what you need to do in the next couple minutes. Make good choices. Work on physics. That's what I'm going to say.
So I redid this lab.
Hold on just a second. Let me just stop this. Not because I don't want to talk to you, but